Hello and welcome friends. In this particular module, I wish to discuss about operation and design of cyclone for control of the particulate matter. In this particular presentation, we'll discuss about working principle of cyclone, typical control parameters, classification, applications, standard dimensions, theory of cyclone, efficiency and factors affecting efficiency, and approaches for analysis. As you learn the content, you will be able to explain working principles of cyclone, explain theory of cyclone, and also design a cyclone for desired efficiency. Let's try to understand how this particular centrifugal force is advantageous over gravitational force. As we discussed in the last presentation, gravity settler is not advantageous as far as industrial applications are concerned. Hence, we wish to employ the centrifugal force. As you have learned already, the centrifugal force is caused when particle moves along the curvilinear path and it tends to move that particle in straight line. In order to understand this particular power of centrifugal force, let's assume a particle moving along the circular path of radius 0.3 meter with a velocity of 20 meter per second. Here, the ratio of centrifugal force to gravitational force can be put up as shown here. So, the centrifugal force would be given by mv square by r, whereas gravitational force is given by mass into gravitational acceleration. For the data that we have assumed, this ratio works out to be around 136 times. Hence, the centrifugal force is too large as compared to gravitational force. Hence, it can be used beneficially in order to cause the removal of still finer particles which are not removed through simply gravity action. As we consider the Stokes expression, you already know that the settling velocity, terminal settling velocity, can be given as gd square rho p divided by 18 mu. As we consider the movement of the particle along the curvilinear path and this particular Stokes rejoin, this gravitational acceleration can be put up in terms of centrifugal acceleration, which is given by this vi square by r. So as we substitute this g with vi square by r, we'll be getting this revised settling velocity that will be applicable when we consider the centrifugal force. The equipment that we wish to design by making use of this centrifugal force in order to cause the particulate removal is called as cyclone. Essentially, the cyclone is centrifugal separator. It is inertial type of the separator. However, the force causing this particular separation of the particulate is centrifugal. As you see in this particular sketch, the upper portion is cylindrical, whereas this lower portion is inverted truncated cone. As there is gas inlet here, dust laden gas enters into this particular circular body, it moves in the downward vortex, and accordingly the particulates are separated because of the action of the centrifugal force and removed through this lower hopper. Here, this particular equipment is very advantageous as it is simple in construction as well as it has lower cost implications. Also, as there are no moving parts, the Cyclone proves to be virtually maintenance free. It also requires the less floor space, and the properly designed Cyclone can be operated at very high pressure as well as even at high temperature. So as we got introduced with the constructional aspects and how that particular particle is getting removed, we will further elaborate on that. The steps are shown here. This is step 1. So particular laden gas is forced to move in a vortex by mechanical arrangement of that axial plates. So as this particular gas changes the direction, the centrifugal force that is induced on that particular particles causes that particle to move in the radial direction and hence bombard on the body of this particular cyclone. As it is bombarded on this particular body, it loses its inertia and accordingly it gets removed through the hopper that is placed at the bottom. Here, this particular cleaner gas now rises through this particular center with some inner helix, and as it moves up, there is a provision of outlet, and through that particular outlet the clean gas is discharged into the atmosphere as per the requirement. While designing the cyclone, we have to think of certain control parameters. Here the velocity of inlet gas could be 15 to 20 meter per second. The number of the vortex that are formed in the circular and that conical body could be 5 to 6. The diameter of the cyclone could be maintained to be 15 to 30 centimeter. The flow capacity is maintained within the range of 0.15 to 0.225 cubic meter per second. The pressure drop is given by this particular expression. Typically, it is 10 to 20 centimeters of water. The category of the cyclones can be considered in terms of the performance as well as even the way we feed that cyclone. So, as shown here, there could be 3 categories of the cyclones. The first one is high efficiency. So, this particular cyclone will be having the diameter less than 30 centimeter. It is characterized by high pressure drop, but it has got very good collection capacity, could be helpful even to remove the particle having less than 10 micron size. Another category is high throughput. In the first category, that is high efficiency, we cannot handle high magnitude of gas. Whereas in this particular high throughput, here we are not much bothered about the efficiency, but we wish to have handling of higher volumes of the gas. Hence, the diameter could be maintained more than 1 meter. It is characterized by the low pressure drop as well as high flow rate, and this would be helpful in order to remove the coarser particles which are having the diameter more than 30 micron. Whereas the third category is conventional one. It is intermediate to high efficiency and this high throughput. Here, this particular conventional cyclones are helpful with the optimized performance and hence are conventionally chosen. Also, the way we allow the entry of the gas and hence the particulate within that particular cyclones, we can have the classification as involute type, when axial type and multi-clone type. In the first category, as you see, there is a tangential gas inlet which is rectangular in cross section and it blends gradually with the circular body of that cyclone cylinder. So it is equipped with that 180 degrees involute in order to have that kind of a blending and hence the name involute cyclone. Whereas, as you see in the second category, there are certain axial inlets which are fixed in nature and that facilitate the spiral flow. So here the ring of the bends around an inner cylinder imparts the circular motion. Now as we consider this particular individual involutes or the when axial, the way we consider about the high efficiency or the high throughput, here as we have these involute or when axials as individual, they won't be able to handle the high volume of the gas. Hence, series of such cyclones are housed together in a common body. So there would be some common inlet that is meant for these particular housing so that these particular cyclones would be acting parallelly and accordingly they will cause high handling as well as also the better removal. As there are multi-clones, here this is called as multi-cyclone. As we discussed previously, this equipment is easy to install. The maintenance is less, it is quite sturdy, it can be operated at higher temperatures. Even the construction cost is less, the footprint is small. Hence, such kind of the equipment can be used conveniently as certain, say, pre-cleanser. If we wish to have some high-end efficient devices like ESP or the bag houses, which we will be discussing later. These particular equipment are very successfully used in the various industries like grain mills, cement plants, fertilizer plants, etc. Here, these cyclones which are conventional in nature do have certain standard dimensions. The way we discussed previously, the cyclone type could be high efficiency, it could be conventional, it could be high throughput. So here, based on the research that is carried out by Shepherd and Lapel, the optimal dimensions of the cyclones were decided. The subsequent researchers contributed further, and accordingly all dimensions of the various parts like body diameter, height of the inlet, width of the inlet are decided essentially in relation of this particular body diameter only. So as we see here, this for conventional cyclone, the height of inlet, which is h, can be zero point 0.5 times d, the width can be 0.25 times d, and accordingly all the components in proportion with this particular body diameter. Let's try to understand theory pertaining to the working of this particular cyclone. As we see in this particular model, the gas spins through n rotations in this outer vortex. This value, which is nothing but the number of that particular rotations, can be given by 1 by h into bracket LB plus LC by 2. Here this h is height of the inlet duct, LB is the length of the cyclone body, LC is length of that cyclone core. Now, in order to have that particular particle collected, it must strike the wall within the amount of the time that the gas travels in this particular outer vortex. This gas residence time in this outer vortex can be expressed as a delta t, and it is nothing but path length divided by speed. So here the path length is nothing but pi d times m divided by vi. So here this d is cyclone body diameter, n is number of rotations the way we discussed earlier. This vi is gas inlet velocity, which can be further given by q by wh. So here this q is volumetric flow rate, could be expressed by meter cube per second. W is the width of that particular inlet, whereas h is height of that particular inlet. The maximum radial distance traveled by any particle is nothing but the width of that inlet duct. The centrifugal force quickly accelerates the particle to its terminal velocity in the radial direction, with the opposing drag force equaling this centrifugal force. The terminal velocity that will just allow a particle initially at a distance of w away from the wall to be collected in time is Vt is equal to w by delta t. Here, the way we deduced initially, this Vt is a function of this particular size. So, as we consider this Vt multiplied with that residence time, it is nothing but the width that is to be covered in order to reach the inner surface of that particular cyclone. As we discussed on the last slide, it can also be given, this delta t can also be given by pi dn divided by vi. Hence, this Vt can be expressed as Wvi divided by pi dn. So, as we compare these two expressions, the diameter, which can be removed with the 100% efficiency, can be worked out by making use of this particular expression. So, it is worth noting that this expression helps us to work out this particular dP, which is size of the smallest particle that will be collected if it starts at the inside edge of the inlet duct. Thus, in theory, all particles of size dP or larger should be collected with 100% efficiency. So, as we consider certain ideal conditions, which won't be always true, because this collection efficiency depends on the various parameters. However, as we consider this particular particle size to be collected with 100% efficiency, which is highly impossible. Hence, as we deal with this particular theory, Lappel in 1951 has developed the concept of 50% cut diameter, and accordingly the expression given is dPc as 9 mu w divided by 2 pi nvi rho p minus rho a raised to 1/2. Here, as you see, the way we deduced the expression on earlier slide and the way we are considering this particular cut size diameter concept, here there is only involvement is nothing but the factor 2 in the denominator. As we discussed about the gravity settling chambers, the fraction captured was put up in terms of the efficiency and given by L times Vt by HV average. As we consider the Stokes expression for Vt, we get this particular expression. However, as we consider for this particular cyclone, here the V average is nothing but the inlet velocity. The gravitational acceleration is to be considered with this particular centrifugal acceleration. Here, in order to avoid the confusion with the capital D, which is diameter of the particle, with the cyclone body diameter, we are considering it as dP. Radius r is considered in terms of the half of the diameter of the cyclone. Also, the maximum length that particle can travel through that particular cyclone is nothing but pi d naught times n. Also, the height is wi. Hence, as we consider this particular terminology and as we put up in this particular expression, we get the expression for block efficiency as shown here. The way we discussed about the gravity settling chamber in earlier presentation, the efficiency for mixed flow can be put up as 1 minus e raised to minus eta block. So, this is the expression that we have deduced in order to work out the efficiency for the cyclone. Hence, we can have now consideration of factors which are affecting this collection efficiency. So, the cyclone efficiency increases with particle diameter, inlet duct velocity, also the cyclone body length, the way we considered in terms of that number of revolutions which are causing, and the pi times d. Also, the ratio of cyclone body to body diameter to gas exit diameter, the dust loading and smoothness of cyclone inner wall. Also, we can consider the factors which can adversely affect the efficiency. So, if the gas is viscous in nature, it will cause the sticking of the particulate, bulky movement, and hence the particulate won't be getting removed easily from that particular gas stream. Also, if the body diameter is higher, the particle has to travel higher W, hence the larger time in order to reach the surface. The gas exit diameter, gas inlet duct area, and also the gas density, which are factors which are adversely affecting the efficiency of cyclone. In order to understand this determination of the efficiency, we can also go for the graphical solution suggested by Lapper. So the way you see here, we have the graph which is efficiency versus ratio of particle size dp to cut size diameter. So as you see here, for one, which is nothing but dp is equal to dpc, we are getting their particles are removed by the 50% efficiency, and hence this is the cut diameter. Now, if for a given particulate which is varying specific diameter, as we compare with this particular dpc, and for that we can simply work out the efficiency by using this particular graphical solution. Subsequently, Theodore and De Paula have fitted certain algebraic equation to this particular curve, and accordingly here this expression can be used in order to work out the efficiency. So the application of which we'll be discussing on subsequent slides. So in order to design a particular cyclone, we have to have the size analysis of the dust particles which are present in that influent gas stream. We must have the particle cut size diameter, which is getting removed by the 50% by mass expressed as d50. So as we have this particular data, we can assume the cyclone diameter, and by making use of the expression for d50, we can work out that cut size diameter. So if the calculated d50 does not match this particular desired d50, we'll go for the next trial and the calculations will be repeated. So after establishing this particular cyclone diameter, the removal efficiency of these dust particles which are having diameters other than cut size diameter can be estimated by making use of the graphical solution suggested by Lapple or the expression which is given by Theodore and De Paula. The overall efficiency of the proposed cyclone is calculated using the relationship as given here. So let's try to understand the use of the expressions that we deduced in this particular presentation. So for a given data here, determine the particle removal efficiency. The air stream with a flow rate of 7 meter cube per second is passed through the cyclone of the standard proportions, and the diameter of the cyclone is 2 meter. So here there are two heads. The first is particle diameter is 10 micron with density of 1.5 gram per centimeter cube, and the second one is 64 cyclones. So we have to do the calculations for multi-clone. So let's attempt this particular first A part. So as we have the standard proportions, this W can be expressed as 0.25D. This H can be expressed as 0.5D. So for a given D here, for a given 2 meter D here, this W comes to be 0.5 meter and H comes to be 1 meter. For a flow of 7 meter cube per second, and for W and H computed here, Vi works out to be 14 meter per second. For the given combinations, we can make use of the expressions, or otherwise the value of the N is given as 5. Mu is 2.1 into 10 raised to minus 5. So as we make use of this cut size diameter, it works out to be 12 micron. Here, this 12 micron size can be used for this particular graphical solution, or otherwise we can go for Theodore expression, and accordingly we can work out the efficiency, which works out to be 41%, whereas the expression that we deduce for the block flow gives the exact value of 35%. Similarly, as there are 64 cyclones here, by making use of the particular, by making use of that cyclone diameter, we can work out WH here. The area of individual inlet could be 7.2 into 10 raised to minus 3 meters square. As there are 64 cyclones, the total area works out to be 0.46 square meter. For a given case, inlet velocity can be worked out as 15 meter per second. Here, as we go for this particular expression, dPc works out to be 4 micron. So we can follow the same alternatives here. We can go for the expression for dPc, we can go for the graphical solution, and this efficiency can be worked out as 86%. As we discussed on the earlier slide, the overall efficiency, which is nothing but the performance of the cyclone, is weighted average of the collection efficiencies for the various size ranges. So it is given by eta is equal to sum of eta j mj divided by m. Here this eta is overall collection efficiency. Mj is the mass particles in the jth size range. This capital M is total mass of the particles. So for this particular given data, this N is worked out as 6, inlet velocity is worked out as 20 meter per second. The cut size diameter is worked out as 5.79 micron. Here, as you see this particular tabular statement, the size ranges are given. So average particle size we can have. For that particular average size, by making use of ratio of D to dPc, we can go for the graphical solution and the individual collection efficiencies can be worked out. The mass fraction can be worked out as individual fraction divided by total fraction. So accordingly here, this M by M can be used further in order to have the contribution to the performance of that particular cyclone. So as we sum up that particular values, here what we get is nothing but the overall efficiency. For the given data, it works out to be 70.6%. Another data, a conventional cyclone separator is to be designed for removing the 50% of the particles having diameter 5 micron. So the cut size diameter is 5 micron. The particular density is 2000 kg per cubic meter, which is flowing with a rate of 2 meter cube per second. N is given to be 5, mu is standard value for the given temperature range. So the WH can be worked out by making use of that conventional standard proportions. So the inlet velocity Vi can be worked out in terms of d here. So as we make use of this expression for this dpc and make use of given diameter, the diameter of the cyclone body can be worked out as 0.8 meters. I hope the discussion that we tried to have for the cyclone is clear to you. So, we can understand now the approaches for analysis. The way we discussed about the previous slide, we can have the performance analysis. So here, all the parameters and the dimensions for the existing cyclone is known to you, and hence the efficiency is to be calculated for that particular situation. Another approach can be, we wish to install the cyclone for a given situation. So we have to assume certain target performance. For the design airflow particulate size, its mass distribution, we can adopt whether to go for, say, high throughput, high efficiency or the conventional cyclone, and then the sizes can be worked out based on the trial and error to achieve the desired efficiency by making use of the expressions that we discussed in this particular presentation. So, thank you for your attention, friends. I hope the concepts that we try to discuss are clear to you. You can simply ask the doubts you have over my channel. Now, in the next presentation, I wish to discuss about the operation and design of weight collectors. So, bye till then, I wish you very happy learning. Thank you.